Hello everyone, I'm Wunan Guo from Fudan University. I'm gonna present our work, detecting and fixing data loss issues in Android apps. First, let me explain what is data loss issue. Data loss issue is a phenomenon that Android apps behave unexpectedly due to the loss of program variable values. Look at this example. This is the item edit page of the app Bcount, a knitting project helper on the Google Play. The two pictures on the left and the right are what the page looks like before and after it is rotated. We can see that the user date in the green frames is lost after rotation. The number 1 becomes number 0 and the text node becomes empty. Data loss is extremely pervasive. A recent study reported that about 88% apps had data loss issues. Data loss can lead to poor user experience and thus affect the popularity of the app. Fixing data loss issues automatically is non-trivial. A strawman way to fix data loss issues is to save and restore all variable values in an app page. The problem with this way is data oversaving. An app page may comprise a large amount of data that is irrelevant to user input. Saving this irrelevant data could slow down the app. Look at this page. It includes 17 widgets and each widget contains more than 15 properties. It contains 311 variable values in total. In this way, all the 311 variable values will be saved. However, there are only 5 variable values need to be saved. A recent work, LeafDroid, uses static analysis to reason about program variable and GUI properties that might be changed during user interactions and save them. For the example just mentioned, 166 variable values will be saved by LeafDroid. Although a significant portion of variable is ruled out in static analysis, LeafDroid still suffers from the oversaving issue. To eliminate the oversaving issue, we present a technique called iFix data loss. The key side of it is that the scenarios in which data loss issues occur can be simulated by generating a particular event or composed event during testing. For example, screen rotation can be triggered by executing an orientation change event at app runtime. Thus, we can detect data loss issues by testing each app page for these data loss scenarios and checking if data is lost. For the example, iFix data loss save and restore 5 variable values. Now, I'm ready to introduce our approach. It includes 3 parts: data loss reviewing strategy design, data loss issues detection, and data loss issues fixing. This is the activity lifecycle diagram. The rounded rectangle represents the state of the activity. The methods on the edge represent the callback methods to be invoked when the activity goes from one state to another. Data loss is a state inconsistency issue that occurs in activity recreation. So, to identify all data loss scenarios, we need to find all paths from the resumed state to the shutdown state. As shown in the lifecycle diagram, there are 4 paths. They are S1, on pause, on save instance state, on stop, S2, on pause, on stop, on destroy, S3, on pause, on save instance state, on stop, on destroy, and S4, on pause, on stop. However, according to the Android documentation, the onStop callback method marked by the dashed line occurs only when the back button is pressed. Subsequently, the onDestroy callback method is called. Therefore, the S4 cannot occur, and only S1, S2, and S3 can occur in real-world scenarios. For the three scenarios, S1 often occurs when an activity is forcibly killed due to the interrupter actions, for example, being killed by the user swiping or killed by the Android system. S2 occurs when an activity is destroyed by the user pressing the back button or the activity finishes itself. S3 occurs when an activity is destroyed and recreated due to runtime configuration change, for example, screen rotation. So, we use kill, back, and rotate to simulate the three scenarios. This is the overview of our approach. It includes two steps: data loss issue detection and data loss issue fixing. Given an APK under test, iFixDataLoss first uses static analysis and dynamic exploration to identify activities in the app that have data loss issues. For each activity that has a data loss issue, iFixDataLoss uses a template-based approach to generate a patch to fix the data loss issue. Lastly, iFixDataLoss runs the app and explores the patched activity to check if the data loss issue is correctly fixed. For the data loss detection, iFixDataLoss first builds an activity transition graph by performing static analysis on an app under test. Guided by this graph, iFixDataLoss mimics user actions to exercise the app with a guided exploration strategy that steers the exploration towards a page that may be affected by data loss issues. For each app page, iFixDataLoss executes a set of predefined events that are kill, back, and rotate to create data loss scenarios and test the page in these scenarios to find the data loss issues. For the data loss fixing, we first introduce three templates derived from the Android documentation. This template is used to save and restore persistent date. The Android documentation suggests saving this kind of date in onPause method and restoring it in onResume method to ensure nothing is lost in case the current activity is killed. To keep the methods onPause and onResume fast, we adopt the shared preference to save and restore date since it is relatively lightweight compared to databases and file systems. This template is used to save and restore date in a single app ROM. As suggested in the Android documentation, we save and restore this kind of date in onPause and onResume method respectively. Since it is date for a single session, we save it in the bundle object that is used for passing date between Android activities. This template is used to save and restore various of non-edible widgets. The Android documentation suggests saving and restoring them using onSaveInstantState and onRestoreInstantState methods. For the patch generation, given a set of variable v whose values need to be saved, iFixDataLoss first divides them into two categories: v-edible, that indicates the variable storing values of edible widgets, and v-non-edible, that indicates the variable storing values of non-edible widgets. V-edible are further divided into two categories: v across app ROM, that indicates variables whose values are used across app ROMs, and v single app ROM, that indicates variables whose values are used in a single app ROM. For each category of variables, iFixDataLoss uses the corresponding templates just mentioned to generate code for preserving their values, and then it assembles the code to generate a patch. To evaluate a patch, iFixDataLoss runs the app and tests the patch activity in all 3 data loss scenarios to check if any data loss issue is found, and systematically explores functionality related to the activity to check if any crashes or freezing issue occur. If no error is found, iFixDataLoss outputs the patch. For the evaluation, we answer 3 research questions. The first one, effectiveness of data loss issue detection. The second one, patch quality. The third one, usefulness. We evaluated iFixDataLoss on a dataset containing 66 Android apps. It includes 21 benchmark apps used in LiveDroid, 48 apps in DLD, and 4 apps downloaded from the Google Play Store. These 4 apps were used for data loss issues investigation during the early study. For the first research question, we compare iFixDataLoss with LiveDroid and DLD. The number of data loss issues detected by each tool are shown in the figure. It can be seen that iFixDataLoss significantly outperforms the state-of-the-art techniques in terms of the number of detected data loss issues. For the second research question, we evaluate the quality of patches generated by iFixDataLoss and LiveDroid. We classify patches into 4 categories based on whether all data loss issues are fixed and the false positives. The 4 types of patches are from the best case to the worst case. Type 1 is the best case. Type 2 is worse than Type 1. Type 3 is worse than Type 2. And Type 4 is the worst. The number of patches of each type generated by iFixDataLoss and LiveDroid are shown in the table. It can be seen that iFixDataLoss outperformed the state-of-the-art technique LiveDroid in terms of the number of fixed data loss issues and preserved false positives. For the third research question, we selected the top 10 apps in the dataset that have been updated most recently and submitted all the patches for these apps to developers. In total, we created and submitted 20 pull requests on GitHub. Out of the 20 pull requests, 16 have been accepted with very positive comments. In this paper, we introduced a practical technique iFixDataLoss that can automatically detect and fix data loss issues in Android apps. Our extensive experience shows iFixDataLoss is effective in detecting and fixing data loss issues in Android apps. Thanks.